In this video, we're going to cover sections 4.5 and 4.6, which deal with the conformations of alkanes, specifically ethane, propane, and butane. And we're going to be using Newman projections to show the various conformations that these alkanes can form as a result of that free rotation that occurs between carbon-carbon single bonds. So in this example, we're looking at a particular conformation of ethane, like we saw in the previous video, where the carbon-hydrogen bond in front, highlighted in red here, this hydrogen in red, this bond with respect to a carbon-hydrogen bond in back, attached to the back carbon, we see that there's a particular angle associated with how these carbon-hydrogen bonds are found in three-dimensional space. And so this is known as the dihedral angle. And for this particular conformation, this dihedral angle is approximately 60 degrees. And so what we're going to look at is if we rotate one of the carbons in front or in back, but if we rotate one of the carbons with respect to the other, we're going to see how this dihedral angle will change and how that dihedral angle and the interactions that occur as a result of how these bonds are arranged in space, how they affect the overall energy or stability of a particular conformation. There are an infinite number of possible conformations for ethane, but the two most important ones are the lowest energy conformation and the highest energy conformation. So again, there is complete rotation available around that carbon-carbon single bond, but we're just going to focus on the highest energy and lowest energy conformations for this alkane. So as you can see, the lowest energy conformation is referred to as the staggered conformation. The staggered conformation, the dihedral angle, as we saw in the previous slide, is 60 degrees between the carbon-hydrogen bond in front and the carbon-hydrogen bond in back. The highest energy conformation, the least stable conformation for ethane, is when you have direct overlap of the carbon-hydrogen bonds in front with those in back. And I realize that in this particular depiction of this Newman projection, we're not showing those carbon-hydrogen bonds directly overlapping. If we did so, we would not see what is attached to the carbon in back. And so we show them slightly to the left as depicted here to show that eclipse conformation. So we draw them as close to one another as possible, but for clarity, we still have to separate them a little bit so we can see exactly what is attached to those bonds to the carbon in back. So this eclipse conformation will be the highest energy conformation, the least stable for ethane. Now we can map out how the energies change as we go from that staggered to eclipse conformation using these potential energy diagrams. So this diagram, or graphical representation of these conformations, we're plotting the potential energy, the relative energy of these conformations against a particular dihedral angle. And the dihedral angle that we're concerning or looking at is the difference between this carbon-hydrogen bond to the carbon in front and this carbon-hydrogen bond to the carbon in back. And so what this graph is showing is that as we rotate this particular carbon-hydrogen bond in a clockwise manner, as we rotate it by 60 degrees with each rotation, we're going to look at the conformation that results from that 60-degree rotation. And as you can see, when we go from the staggered conformation, if we rotate by 60 degrees, we end up with an eclipsed conformer. So we have an eclipsed conformer dihedral angle of 0 degrees, and this represents a high energy conformer. And so as shown, it's going to have a high potential energy. It's going to be the least stable conformation for ethane. Now, if we continue to rotate the carbon in front by yet another 60 degrees, we're going to end up with this particular conformation. And so now you can see the dihedral angle between those two carbon-hydrogen bonds has been reduced to 60 degrees. And again, we have a staggered conformation. And so again, similar energy, same exact energy actually as that original conformation. And so again, with another 60-degree rotation of the carbon in front, we go back to an eclipse conformation. We continue to rotate, staggered, eclipsed, and then finally staggered. So as you can see, all the staggered conformations are identical in nature and have equivalent energy as well. The eclipse conformations are all identical and have similar energies. And so the differences in energy between the staggered and the eclipsed has everything to do with torsional strain. So torsional strain is strain that is experienced by a molecule when the electrons found in the carbon-hydrogen bonds interact with each other through space. And so ideally, the electrons in those carbon-hydrogen bonds like to be separated by this 60-degree dihedral angle, but when that dihedral angle drops to 0 degrees, you can see how the energy of that conformer increases. We say that the torsional strain is the reason behind this increase in energy. Steric strain, which is associated with bringing atoms into close proximity to one another, isn't really, it's minimal, or we often say it's non-existent in this ethane example because the hydrogen atoms are so small. But we'll see in the butane example, when we have larger groups interacting through space, there's an additional strain associated with that, and we refer to that strain as steric strain. But at this point, torsional strain is the strain that's associated with this difference in energy. So for propane, the situation is very similar. It's just that now with propane, we have a methyl group associated with one of the carbons. In this example, what we're looking down is this particular carbon-carbon single bond. And so we're looking at rotation around this particular carbon-carbon single bond. So that rotation around the C2, C3 is what these conformations are representing. So if we start with the staggered conformation for propane, here we see we have the methyl group attached to the carbon in front, and we're going to rotate that methyl group in a clockwise manner and observe how that changes the conformation of that Newman projection for propane. So as we rotate that by 60 degrees, we see that we end up with a eclipse conformation. Okay, and so the torsional strain associated with the overlapping carbon-hydrogen bonds, both in front and back, and that carbon-carbon bond for the methyl group with the carbon-hydrogen bond in back, there's going to be additional torsional strain associated with that. And you can see it's very similar to what we saw for ethane, just a couple kilojoules greater. Now, as we rotate an additional 60 degrees in the clockwise manner, we return to a staggered conformation. And so like we saw with ethane, we're going to go from staggered to eclipsed, back to staggered, eclipsed, staggered, eclipsed, staggered. And so those are the two high and low energy conformations. The eclipse being the highest in energy, least stable, and the staggered conformation being the lowest in energy and the most stable conformation for propane. So again, torsional strain is the predominant factor that is responsible for the difference in energy as we go from staggered to eclipse. Now, when we go to butane in section 4.6, the situation is a little bit different. That we're going to have different energies between different types of staggered conformations, and we'll also have differences in energy between different types or labels that we use to describe eclipse conformations. So let's look at butane. So butane, but represents 4 carbon atoms, alkane, and in this example, we're looking down again, the C2-C3 bond axis. And so to the carbon in front, we have a methyl group, and the carbon and two hydrogens, and the carbon in back, we also have a methyl group and two hydrogens. And so the first conformation that we'll look at is a staggered conformation where the two methyl groups are 180 degrees apart from one another. So the dihedral angle between those carbon-carbon bonds, both in front and back, is 180 degrees. So as we rotate the carbon in front, so as we rotate this group, or this carbon, I should say, and all the groups attached to it by 60 degrees, we come to this particular eclipse conformation. And in this eclipse conformation, it is, again, predominantly torsional strain associated with the carbon-carbon bonds in front and the carbon-hydrogen bonds in back. So as we rotate further at an additional 60 degrees, we end up with this particular staggered conformation where the two methyl groups are in fairly close proximity to one another. So the carbon-carbon bonds in front and back, the dihedral angle between those are now only 60 degrees. And so there's an additional steric strain associated with those two methyl groups coming in close proximity. And so we see that there's an additional energy. It doesn't come back down to our original energy. There's an increase in energy by about 4 kilojoules per mole associated with this particular conformation. And as we'll see, we're going to refer to this conformation as the gauche conformation. And this will be referred to as the anti-conformation. So we'll talk about that on the next slide. As we rotate further, another 60 degrees in a clockwise manner, we're going to come to a conformation in which now we have another eclipse conformation, but now these two methyl groups are lying directly behind one another. So in front, they're directly overlapping. And so this is referred to as the least stable of all the conformations for butane. This is sometimes referred to as eclipse 2, and just to designate something different from these two eclipse conformations. But these two eclipse conformations have a slight difference in energy, 3 kilojoules per mole, in fact, because of the placement of these two methyl groups lying directly over one another, or directly through space on top of one another, if you will. So this is the highest energy and least stable conformation for butane, when you have those overlapping methyl groups through space. As we rotate another 60 degrees, we can see we return to this gauche conformation. Again, these are all your staggered conformations. These are all your eclipse conformations. But with butane, because of the additional strain associated with bringing those two methyl groups into relative proximity to one another, we have additional terms to describe those different states. So the staggered conformation with a dihedral angle of 180 degrees, we refer to this as the anti-conformation. So when the methyl groups are farthest apart, we refer to this as the anti-conformation. Now, as I just mentioned, when those methyl groups are 60 degrees apart, there's going to be what we call a gauche interaction. So we refer to this conformation as the gauche. So the gauche interaction is a steric interaction that results when the two groups in a Newman projection are separated by 60 degrees. So the dihedral angle is 60 degrees for those two carbon-carbon bonds. And so we refer to this as gauche, and this is anti. And you can see that there will be multiple gauche possibilities in the conformation, and they experience the same type of steric interaction, and so their energies will be equivalent. Now, similarly, the eclipse conformations, they're not identical in energy due to the fact that there's additional steric hindrance associated when you have two methyl groups directly overlapping in space versus the two methyl groups that are neighboring one another with that dihedral angle of 60 degrees. So just as we saw that there are differences in energy between these two staggered conformations, the anti and the gauge, there's also a slight difference in energy between eclipse 1 and eclipse 2 due to the differences in steric strain or steric hindrance associated with those methyl groups. So I'll just write that in. We often refer to this as the eclipsed one, as well as this particular system, and this system we refer to as the eclipse 2, just to designate that those are different conformations for butane. So that's all I have to say about the conformations of alkanes, specifically today for ethane, propane, and butane, but we can apply this similar type of strategy to other alkanes as well. So if you have any questions about the conformations of these alkanes, send me an email, set up a Zoom appointment, or start a discussion in our forum. Thanks.